Okay, hi everyone. This is the last lecture in distributed systems for this year. Woohoo! This one is about content delivery networks, and as I've reminded you every time, I am not, in fact, Bjorn Frankie. These are his slides. I am Hugh Leather, and I will do as well as we can. So, content delivery networks. We're going to talk about why you need them. We'll talk about edge servers, what they are, how one actually delivers the content through the content delivery network, how to map information around, and what this has done to the internet as a whole. What is a content delivery network? Essentially, the idea is this, that if you are a provider of content, it is more efficient for you to make sure that your content is available near to your users than just to have a single origin server. This means that you need to have machines set up in different parts of the world near to where all your users are, and that infrastructure is expensive to create. Fortunately, there are existing content delivery network companies, who already have this infrastructure and will essentially provide it to you as a content provider yourself. So some CDN company has hundreds or thousands of these CDN servers throughout the world close to users, and you as a content provider will tell them what content you have, and it will be uploaded to their servers and distributed throughout the world, enabling fast replication and access for your users. The kind of reason why we need this kind of thing is that there are times when various websites are hit hard. An example given here was that during a US presidential election, there is a huge amount of web traffic to news sites. Those sites might not be able to provide enough bandwidth to be able to serve up what the number of users that are coming to their sites. CDNs allow that those content, those news sites, etc., not to have to worry about it. And we'll see how soon. So here is a case study from the 2000 election. And what you'll see is that at some point during the night of the 2000 election, in the US this is, the news organizations' servers started to have too many requests coming to them and would have fallen over. AKAMAI, which was at the time, well, and still is perhaps the most significant content delivery network provider, their servers were able to take the load and meant that the news organization servers did not fall over instead, and were instead able to continue delivering news throughout the night. So what is the content delivery network? Essentially, the idea is that there are caches of content that work closely with the internet service providers to install information close to the customers. So when a customer requests a page, the ISP will first route them to the CDN, if appropriate, and if the information can be given to them from that close server, then the request does not need to go all the way across the world to the actual company whose website they are thinking they would like to access. This makes the total amount of traffic on the web lower and means that users get far better response times than they would do if they had to travel to the other side of the planet, even supposing that the machines on the other side of the planet could handle the load. So, the kind of things that are stored on CDNs are video, websites, JavaScript files. You will see that, for example, things like jQuery, which is a bunch of JavaScript that is commonly used in websites. These are often downloaded from CDNs so that the jQuery producers don't actually have to have so many servers in order to provide the load that millions of websites wanting to download jQuery would create. There are some issues in that you need to work out where data should go, what information should be on caches, how long to keep it there, which server is appropriate for each user's request, and so on. Proximity is not the same in the network as geographic proximity, because instead it requires you to think about how long it takes information to travel, and information travels at different speeds depending on the thickness of the pipes. So you can have 2 points that are geographically far away, but by being connected by faster pipes, they can be essentially closer together in network distance. The mapping problem is designed to make the focus is on trying to make the user's experience better. Why do we want content delivery networks? The potential benefits are that you can scale far better than you could before. If the number of users grows in one area of the world, you can install more CDN servers in order to handle that load. And essentially, if arranged decently as a tree or some sensible graph, this can go on infinitely. The good thing about the way CDNs are used is that they are essentially embarrassingly parallel. At a large scale, the infrastructure shared amongst many customers is quite cheap. So although hot sites may use more resources and therefore end up paying more to the CDN infrastructure company, they may not stay hot forever, and multiplexing these things around is done over time as well as different sites. The whole goal of this thing was to reduce latencies, but that also reduces congestion because requests are often serviced earlier. And that means that then there is less traffic through the whole of the internet, meaning that everything else gets faster as well. So to give an idea of the type of thing that you might see on this, CDNs will handle video streaming. You can bet that when Netflix produces the next version of Stranger Things, the next series of Stranger Things, all of that will be distributed via CDNs. I think actually Netflix has its own CDNs for doing this. And these kind of CDNs can be very reliable because they are embarrassingly parallel and they don't need much communication amongst each other. If one of them falls over, another one can pick up the slack quite easily. This also means that when somebody is trying to hit you with a denial of service attack by repeatedly making requests to something, with this extremely reliable and highly scalable architecture, they're quite difficult to attack with DOS attacks. Let's talk about these edge caches a little more. So you probably have for each region a set of caches managed as a cluster, and they may represent some particular functions: streaming of videos, providing of JavaScript, and so forth. When they are designed, availability is a major concern. They have to make sure that these CDNs are up all the time. Why is that? Well, because when a CDN server goes down, the client, which is the user's web browser or whatever it might be, will make a request back to the original server, not to the CDN. Which means that if your CDN goes down, then the people paying you to provide those CDN services are going to suddenly get hit by massive load, which is exactly what they were paying you to avoid in the first place. These systems need to also be redundant at the network level. This is partially to help with the availability. And so one of the ways that you deal with server failures in Akamai is that they have a buddy system where each server has another server that is constantly trying to work out with a sort of heartbeat system whether or not its buddy is alive and servicing requests. If one of them stops, then the buddy will start to take over responsibility as the primary server. This means that any users who are downloading at the time and who are connected to a server that has just died and is now moved over will end up having to restart their download, but hopefully that only represents a few people and they will not really notice. Here is an example configuration. You have some root place for the CDN content distributor where content providers will upload information, upload their content, and that will then be sent out to different surrogate servers in different parts of the world, and from there to yet further surrogates, probably in larger parts of the world, and then users will download directly from the surrogates instead. CDNs do not mean that there are not still further possible bottlenecks. The obvious places for these are the last mile and the first mile problem. The last mile is that at some point there is going to be a cable and a physical wire between the actual user and the rest of the internet, which might be some rather low quality copper. And that can limit the speed with which the user can download whatever it is that they are trying to download. The same problem happens in the first mile, is that if the host of the data, the original source of the data, is not connected by a fast link to the rest of the internet, then that also slows down how much information can get across. The backbone is the sort of main trunk lines of the internet, and depending on what's going on there, you might find that information is slowed down. The peering problem is that as you go through the network, there have to be a bunch of agreements with different providers, and who knows what will always happen at those points. You can get bottlenecks appearing in any of these. So let's look at a logical view of how a content delivery network works. The first thing is that some user requests to download some web content, a JavaScript file, a video, audio, whatever it might be. So they make this request, and because they are going through a CDN, this is directed by dynamic mapping to some edge cache that the ISP has determined is the closest one to them. The edge cache searches its local data, local hard drive, for whatever the content is that has been requested. Now, if it doesn't find it, then it will ask neighboring edge caches to see if they have it. And if they don't, then a request is made to the origin server to get that information. It comes back, is cached, and is delivered back to the end user. So that's essentially what is going on. There are optimizations within that cloud-shaped thing. And the kind of optimizations that we're talking about are created by core hierarchy regions. So whilst there are these small edge regions that serve multiple users, there are then much larger core hierarchy regions which serve multiple edge servers. So when a user requests something from the edge server, if it doesn't have it and none of its neighbors do, then it can be asked from the optimal core region. And that then will go to the origin server if need be. So although this increases the number of hops that may be required, it overall decreases the load, assuming that the caching is worth doing. The core region, because the core region can serve many regions, whilst only making one request to the origin server. Hierarchy reduces the total amount of traffic back to the original server. This is great because the customer doesn't want to have too much traffic coming back to it, because that will increase the amount of infrastructure that they need to provide. It also provides protection against sudden spikes in load, and this can be very important when Microsoft releases a new operating system or so forth, or there are some video files that lots of people want to see. And in turn, this improves the end user response time because the core region servers are placed in very well connected zones. They've got very fat pipes, and their optimized connection speeds are used to then improve response time for the end user. So how do you decide which server information should be sent to and which servers users should make requests from? Well, there are a number of different potentially conflicting goals here. One is that you want to balance load across all servers so that one server does not get hit too much. If it gets hit too much, then the response time will go down. Or it might actually just fall over. So we need to do load balancing. We want to get the best performance to improve the client experience. So this might be based on geography, but probably more likely on round trip time, throughput, and load. All of these things need to be taken into account. And in the worst case, if you cannot get any other node to service you, it needs to fail back to whatever is available. So how do you direct clients to a particular server? Well, as part of the routing, then load balancing is going to be handled by the ISP to some degree. It could instead be done as part of the application, using HTTP redirects to enable different servers to be selected at runtime. Or it could be as naming as part of the DNS servers, which has been done as well. If you use application mapping, then HTTP already supports a way to indicate that a web page has moved. This is by returning a 300 and something response. This enables, by telling you that the website has moved, then the client will make a new request to a different part of the web. So the server receives a request from the client, and when it decides which server is best suited for the particular client and the object, it redirects the user to that, the client to that server. This means that your application can fully make all the decisions and gives you complete control. However, there is additional overhead in that some original servers need to receive the first request, do name lookups, and make all of those decisions. So it can work very well, But on the other hand, as we've just seen, due to the amount of effort that it takes from providers, then there are downsides as well. So we have seen how applications can do the mapping themselves. You can also do it through DNS, through name-based mappings. So when the client does a name lookup for a service, the name server itself can decide which server to return. So it can do this by returning the A records, which is one of the types of records that DNS returns, describing the best one for the particular client. To do this, it needs to know the server loads and locations, which have to be collected from somewhere, and it has to have some algorithm for working out which server to use. What are the different mapping algorithms that are used? Well, there are three components to finding which is the closest edge cache to a particular end user. That is to work out based on the expected packet loss, throughput and latency. And then there is, these are listed in order of their importance, roughly. Mapping also takes into account the edge cache performance. Does a server have the object on its hard drive? It uses consistent hashing, which I think has been covered in an earlier lecture. Just in case it hasn't, the idea behind consistent hashing is in order to make sure that when servers come up and go down, that you don't have to rebalance all of the mappings, the user to server mappings that you've got. It arranges them in a circle, and each server has multiple points along the circle, so that on average, when one of them goes down, things only move along to the next server, and only a small number of resources get moved between servers. I think Rick has talked to you about consistent hashing there. And then, does the edge cache have sufficient CPU, RAM, and bandwidth, etc., available to serve the end user? So let's see how this compares to life without CDNs. Here, the user makes a request for some web page, gets that web page, which is HTML that they get back. Embedded in there are a bunch of URLs describing resources that need to be attached to the web page, like, for example, some image. The user's browser then makes further requests, opening those embedded objects from the customer's web server. And that web server has to make multiple round trips in order to serve up the information. Each round trip might take 150 milliseconds or so, and if you're not careful, the entire thing is going to take a few seconds. Instead, Akamai, who was, as I say, the first major company to do content delivery networks, instead, when a URL is requested from an Akamai server, when the client requests when the end user makes a request, it goes through Akamai's local servers, which are much closer to the user. They will often have the content directly there, and they won't have to go to the client servers at all, meaning that everything is much faster. So here are the steps used in Akamai's content retrieval algorithms. So the clients get their HTML from the primary server, and this comes from CNN.com, for example. The web page, the HTML, is modified so that links to content that should be cached by Akamai are replaced with longer URLs, calling out to Akamai, but those URLs contain the original resource URL, as can be seen in this example here. The client then resolves that and can get the content from Akamai. So how do these modified names get resolved? The root server gives the name server record for akamai.net, which in turn gives one for a gakamai.net, which is in the region of the client's server. This has a long time to live because once you've attached a client to the name server, we assume that this is going to be low bandwidth for the user, and we can afford to have that live for a while. But that in turn will give up a smaller server in the region, one that typically has the file in the cache. How do you find that? You can use some hashing mechanism like consistent hashing to find out which one might have it. And then you give a particular name, a hashed name, and this process can have a much smaller time to live because there's more bandwidth involved here, so you want the time to live to be smaller, and each time you can repeat this process more frequently. So here's an overview of how Akamai works, and by extension, most content delivery networks. The end user makes their original request in step 1. They get their HTML page back. They then need to get some resources, the foo.jpg, for example. So in step 3, they ask the DNS root server for the location of the server they want, and they are given that back in step 4. Step 5, they go to the route to the server that the DNS record was told to them that they should go to, which is the first level of Akamai's high-level DNS servers. That then tells you the low-level one in step 7 and 8, and then finally they go to the Akamai server that actually should have the data. And if that does not have the data, it will go back to the original cnn.com to ask for actual foo.jpg. Now you might think this seems awfully involved and that there are lots of requests here, and there are indeed. However, once the end user has found out which Akamai servers he or she should be talking to, then this will get much faster, as we shall see shortly. And indeed, the fact that the Akamai server, the ending Akamai server will then have foo.jpg cached means that it can be served up much faster each time. So when a subsequent request is made, then the user can go to the low-level Akamai DNS server, which will then redirect to local, the one which actually has the resource, and everything will be much faster. And because the Akamai servers have now cached the actual content, they won't need to hit cnn.com again. CDNs have changed the way that traffic moves through the internet. Normally, there are costs to be paid as information moves from one ISP to another. But because CDNs mean that there is less traffic going around, then the costs overall are reduced. The impact of the growth of CDNs has meant that the internet has got flattened. More content is being served from the edge of the network, which is good. It sees reducing load on the core and an increase in peering, and generally is making everything more efficient. But it is also changing economic relationships. So the CDNs are now making money. Akamai is quite a successful company, as are others. ISPs benefit because more content is served locally from them, reduces traffic from the provider and gives them a direct benefit. And users benefit, of course, because of better performance and reliability. The CDNs are sometimes putting caches in eyeball ISPs. What are eyeball networks? That is where users spend more time looking at things on the web rather than creating content themselves. So there are some recent trends in CDNs. CDNs can deploy caches, so other companies are wondering why they can't deploy caches. If you are big enough, then you can go around and ISPs will accept caches from you. If you are the likes of YouTube, for example, I'm pretty sure that they have their own CDNs embedded in ISPs throughout the world. So that has been happening. It enables them to reduce cost, and they can do all the things they need themselves without having to worry about somebody else's servers. And internet service providers are trying to deploy the CDNs themselves. They want to be able to own some of this business themselves and to get money out of it. So to summarize, content delivery networks are improving web performance. Caching only at the client is only a partial solution, and there's not enough locality. So your web browsers already cache a bunch of stuff, but when you are continually traipsing through new content, they're not going to be able to cache very much, although it could be that your neighbors are doing something similar, hence how the content delivery network makes things better. Data being moved closer to the user means that there are lower costs overall and that everything is just more efficient. People are using CDNs for not just static content, but to deliver non-static content as well. Okay, there we go. That was the last lecture. If you have any questions, please send me an email or put something on Piazza noting that it is a lecture question. And I wish you all the very best of luck with the exams and with whatever comes next for you.